Start taking video. I have several comments before starting the lecture. I posted 2 lecture slide set for the topic 3. Okay, so we'll cover that tomorrow. So you get ready for that. All right, and I think most of you are waiting for the homework. So I prepared one for you. So tomorrow I'll assign one homework set, and maybe I'll give you about 10 days to work with that. Okay, and the last comment is, I have one extra handout. I try to avoid this, but somehow new ones are coming up all the time. So I made some 2 extra pages that is related with operation of series resonant converter in strange mode. I think I said several times about the strange behavior of this resonant converter, and we'll cover that. I think we went through this slide, but somehow I could repeat this. This is simple but rather important topic. So what we have here is the schematic of series resonant converter, and I have one notational note. Okay, all the switches in resonant converter, they are bidirectional converter. Okay, but I'm using several different symbols for that. So I just could say this. This is the formal representation of MOSFET switch as a bidirectional switch. So I've been using that sometimes, and in some case, I'll use this symbol, or even I used this sometimes. So all of 3, they represent the MOSFET switch as the bidirectional switch. Okay. Without this body diode, this switch alone is not comparable with resonant converter. So we should have additional current path like the body diode. So that is implicitly assumed when I'm drawing this. Okay. And this slide try to show the relationship between this DC and DC through this AC circuit. So this is the DC input voltage, and this is the DC output voltage. So because you have a capacitor here, so this output voltage can be considered as a DC, right? And with this switching function of this full bridge network, this voltage is transformed to these pulse waveforms, square waveforms, and according to principle of this tank circuit, with the high Q tank circuit, this tank circuit responds only to the fundamental component of these rectangular waveforms, and it will generate current like this, and we have some phase delay in between, depends on the characteristic, the operating point of the converter. We will have a small phase difference, okay, like this, and this is the voltage seen here, okay. This purple color is the real voltage waveform you are watching through the oscilloscope. This is the real current waveforms. You can watch the current proof. So this IT1 first component of tank current, but we assume that only the most of the current is coming from its first component because of the high Q assumption of this tank circuit. So sinusoidal current is coming in, and the sinusoidal current is coming out, because there is one current path, okay? And voltage here is this rectangular waveforms, and voltage at the output is also rectangular waveforms. By the positive current, 2 diodes will be connected, then this voltage is directly applied here, okay? If the other 2 diodes are conducting, negative of this voltage will appear here, okay? So this purple color is the real waveforms, and this is just the fundamental component of these waveforms and these waveforms. You are not watching this. It's just the conceptual description of the fundamental component. Okay? What we are trying to relate, this is relationship between this DC input and the DC output through this AC circuit. Right? So that is shown here. Okay. So we call it DC model, and this is the first of the harmonic model, or AC model, or sinusoidal model, and this is a DC model. So DC is coming in. Right? So if this voltage is Vs, then magnitude of this fundamental component of tank voltage is just using the Fourier series. It's shown here. This is the relationship from DC to AC, and the relationship from DC AC to DC concerns with this current component. So this is the magnitude of fundamental component of tank current, and this is the average current, which is DC. So this is DC, this is the DC. So the relationship is just averaging process. We prove this. So this is the magnitude of this fundamental component of tank current, and this is the average value of current flowing through this. Okay, so this relationship is 2 divided pi with cosine of phase difference. Okay, so this is the story about this junction, and story about this junction is somehow we need to find the relationship between magnitude of this and this value, our voltage value, and the relationship between this tank current and this DC current. Relationship between this tank current, coming out tank current, and this one. So here we have Fourier series again. So this is the relationship between our voltage and the fundamental component of this one. Okay. This is the square waveforms, but we are only considering the first fundamental component. So this is the relationship, and this is the tank voltage. Peak value of sinusoidal waveform magnitude is related with this. Okay. With two relationships, this one and this one, you can define the effective resistance seen at this port, input port of the rectifier circuit, only considering the fundamental component. So this is the ratio of magnitude VR1, this voltage fundamental component, and this one IR fundamental component, and ratio of this is given by this. But this VO divided IO is the output resistance. So the relationship is very simple. This is the real resistance of R, load resistance. You have this magic number, 8 divided pi square. So it turns out this number is 0.8. Okay. So this is the relationship. Okay. So again, here we use the Fourier series analysis. We didn't perform the Fourier series expansion. We just take the result of this expansion, and this is just a simple averaging process. Okay. So what is the use of this? It's very important. So next slide shows that. This is the simplified schematic diagram of previous one. So here we have a DC circuit, and this is VT1. All right. First component of tank voltage. So it's better to move this VT1 here. Okay, V1 is coming in the middle, and this is the relationship between this VR1, okay, fundamental component of this voltage, and this is the VO. Relationship is coming from there. Okay, so first we want to evaluate the DC gain from two output. So DC in, this is the input of this gain M. So this is the input, and this is the output. Okay. There is an easy relationship between these. First, this is the input, okay, Vs, right? If you multiply Vs by this number, 4 divided pi, this is what? This is this one, Vt1, magnitude. So this will give you a number. This number is Vt1, magnitude, okay? This is AC waveforms. So magnitude of AC appearing here is this one. And this is the transfer function from this to that, which is simply transfer function of this tank circuit, evaluate at the switching frequency. If you multiply that, then you will have magnitude of this, VR1. Okay? So this gives you the numerical value of VR1. Okay? And there is a factor of this. If you multiply this number to this. Okay? This is AC. We are talking about the magnitude. If you multiply this number to that magnitude, that transforms to the DC voltage output. Okay? So this is the voltage gain expression about this. This is DC input and DC output. So they cancel. They cancel. Then this ratio between this to this is DC voltage gain is the simply magnitude of transfer function of this tank circuit evaluate at the resonant frequency and using this RE, not R. R is this one, and we need to use RE, which is this, which is 8 divided pi square. So this is the result of this simple analysis. Okay? So you understand this in this manner. That saves a lot of time. If you see other papers or books, they spend many things talking about same thing. This is a basic idea. Okay? So with this, later on, we plot this, okay, magnitude curve from this input voltage to output voltage. AC response is this. Okay? As I said, at the resonant frequency, the reactance of these two reactive components, they cancel. They are not existing, directly connected. Then this voltage must be same as this. So at this, if switching frequency is exactly at the resonant frequency of this tank circuit, this magnitude should be 1, just 1, 0 dB. Okay? And it shows this resonant behavior. And this value is characteristic impedance of this circuit. And we have factor of 20 log QE here. So this is actual gain curve, DC in, DC out. Okay. Suppose you put 10 volt here, the output will be 10, right? And somehow you increase the switching frequency up to here. Maybe this part is 0.5. Then you apply 10 volt DC, then output will be 5 volt DC. That is the meaning of this analysis. So this is called first harmonic model of this series resonant converter. Okay, we just use the input-output transfer function of this tank circuit, but there are other things you can use. Right? First one is this impedance. This input impedance seen by input port of this circuit, and the output impedance seen by this output port of the circuit. It provides some very important information about the operation of this tank circuit. It provides almost the same information about the operation of this series resonant converter. Okay? When you are discussing this, resonant inverter, resonant converter, they are same thing. Just this R is scaled down 0.8 in front, okay, but the other things are the same. Okay? So analysis from here to there, it's just you multiply 8 divided pi, 4 divided pi, something like that. Okay? So this is our final conclusion. As well as the DC gain from the input to output is concerned, you need just evaluate transfer function of this tank and evaluate magnitude at the resonant frequency. That magnitude is the DC in, DC output gain of this converter, okay, which is extremely nice. All right, and I have several pages, but they are not absolutely necessary. You can skip this. Okay, same idea and the same information here. So maybe we set up this fundamental frequency model. So this part is modeled as this DC model, and this is the DC model, and the middle part is modeled as this first harmonic AC model. Okay, this one is also unnecessary, but it's good to know, right? And DC conversion ratio can be evaluated through this very complicated process, but result is the same as the previous one, the much simpler one presented in the second page of this lecture slide. Okay, so the same story, all of them cancels. Okay, this is the conclusion. DC conversion ratio is the same as the magnitude of a resonant tank transfer function. Evaluate at the switching frequency. This one, okay. Most important thing is it really doesn't matter the actual structure of tank circuit. You are using simple RLC combination, but any combination you can find out this. Okay, very easy. Linear circuit analysis. Okay, then you are finding the DC gain of resonant converter, which employs that resonant tank in the middle. Okay, so that is the very important conclusion of this. So we did some analysis about this tank transfer function, evaluate at this resonant frequency. So tank transfer function is ratio from here to there, so which is just the division of impedances. So you have this term in the denominator, R in numerator, this one, and put it standard form. This is the final standard expression for the input-output transfer function. These parameters are predefined like this. Okay, and then DC conversion ratio is this one, magnitude of this. Then you calculate, evaluate magnitude of this, just putting J omega S instead of this S. Okay, then you have this. Okay, this is a general expression. F here is ratio between switching frequency and resonant frequency. This formula says that if the switching frequency is at exactly this resonant frequency, this becomes 1, this becomes 0, and voltage gain is just 1, which is the same as the circuit analysis, not the analysis, just take a look at the circuit, right? And think about the definition of resonance. And you have this. You have this. So this is the repetition of previous result. So this is the final form. Okay. At the resonant frequency, you evaluate this. You put J omega naught here and calculate. Then everything cancels and just 1 remains here. Okay. Or in the resonant frequency, reactance of 2 reactive components, they cancel. So you have just simply gain of 1 at the resonant frequency. This is plot of DC in, DC out gain, which is the same as this transfer function magnitude is shown here, right? For the larger Q means RE is small, right? It works the better tank circuit, then this will be sharp, okay? And at this resonant frequency, gain is always unity, 0 dB line. This is the linear scale, so normalized frequency, twice of the resonant frequency, half the resonant frequency, you have different DC in, DC out gain. Okay, that is the result of previous analysis. Maybe for the first time, it looks complicated. But if you understand the basic things we are talking about, it's very simple. Okay, so you won't forget this if you understand this way. And finally, last week, we discussed this. So one is prediction of this equation, okay, based on the fundamental frequency model, okay. So this blue one is prediction. This is prediction, black square, and white square, the exact response. So we have very close match around this area, okay? So as I said, the larger the QE and closer the switching frequency to the resonant frequency, the prediction becomes excellent, okay? But for this case, Q is reduced to 0.5, then you are seeing some deviation. This is the above resonant frequency operation. So you are having GBS here. Anyway, some deviation is coming up if you decrease this QE, okay? If you further decrease this QE, like 0.2, then the difference will be larger, right? But in the other direction, this is the below resonant operation, maybe GCS region, okay? We only have good accuracy for this only, and if you increase QE to 2, then previously in this region, the deviation is very small, but you are seeing some considerable deviation with this Q. We are talking about the same Q here, but deviation is different. That comes from the nature, strange nature, or eccentric nature of this resonant converter. And one extreme example is this is Q of 0.5. This is a prediction, and the actual response is this one. It's just one. Gain is all the one. We are losing control here. Right? We have the same gain, means the output voltage cannot be controlled by changing frequency. So we are losing control here. Okay? There are big difference and the total difference. This one is total garbage here. Then, okay, I'll explain why this is happening here. Okay? We need some advanced analysis for that, but we'll discuss just result of that discussion. Okay? Details about that. You need some advanced analysis, state plane analysis, phase plane analysis. Okay, so you won't go to that level here. We'll discuss just the result of that analysis. Okay, so this is the review of the previous lecture. So you have new material. Okay, as I said, this model, this is the AC model. Okay, representing the sinusoidal response of the tank network. Okay, difference with the real network is R lead has been modified from the real R. Except for that, this model predict everything about the operation of this resonant tank. Okay, sinusoidal waveforms, but that sinusoidal waveforms can be easily transferred to DC by just scaling the magnitude. Okay, you know that, right? So second one is this one. Previously, we make use of the input-to-output transfer function of this tank circuit, and this time we are looking at this input impedance of this tank circuit seen at this input port, which is this. Okay, input is this one current, and output is this VT1. And it's just the impedance seen in the input port, which is series connection of these three components, which is this. And this is the standard form as this. This is the Bode plot representation of that. So initially, we have integrator here. So this is the integrator. And slope of integrator is this one. And this 0 dB crossover frequency is simply this one, 1 over C. That is extremely easy to see. If you put 1 over C in this place, you are using 1 over C for this S, then everything becomes 0. No, 1. Then that magnitude is 0 dB. Okay? So this is the coordinate of 0 dB crossing frequency. And another one is slope of asymptote of this one. And this frequency is 1 over L for the same reasoning. Two previous one. So we have this. This is the input impedance curve. Okay, this value, we are assuming Q of 1 here, and this value is what? Is a characteristic impedance of this resonant tank circuit. So this is RO. Magnitude of RO, magnitude of L divided by C. Okay, when I put two vertical bar like this, it means magnitude, it indicates 20 log something. Okay. 20 log something is too long to write down every time. So sometimes I'm using just two vertical bar indicating that is the log 20 log scale. So this is the value. And peaking from here, this is the minimum value. Right? When at the resonant frequency, they cancel. That input impedance is just simply RE. So at this resonant frequency, the minimum value should be what? RE. Okay? So RE. For the smaller RE, for the much smaller RE, it comes down like this. Okay? The smaller the RE, this deep becomes deeper, right? That and the resonant becomes, the resonant tank becomes more, the better energy storage element. Okay? So it provides the better performance for the converter. And this value is RE. What I mean by this is 20 log RE, right? And QE, value of the QE. Okay, this term is simply, this is the output, characteristic impedance. So using the notation of This is the written here. Okay. So RO. I wrote down this twice here. One of them is unnecessary. It's called characteristic impedance. Okay. So this is also very important because it signifies this. If the switching frequency is above this resonant frequency, we have GBS switching, right? Because in this region, this has what? Inductive characteristic. Then current is behind the voltage in phase. Okay. In this region, you have this slope, which is capacitive slope. Then everything is reversed. So we have advance current is ahead of voltage in phase. So we have GCS characteristics. All right. Okay. This one is also interesting. Okay. So now we are comparing two tank transfer functions. One is input to output transfer function. The other one is input impedance seen by at input port. So we know the expression of this. This one is this. Okay. Oh, H, not HE. HS, just HS. Okay, forget about this. HES is something else. So use HES. Input to output transfer function of this tank circuit. And expression is this. And this is the tank impedance seen by input port, which is GIS. Expression of GIS is very simple. It's just a series connection of three components. Okay, so this is 1 and this is 2. Then they are closely related. This 1 and 2. Okay, 1 is in the denominator, the other one is in the numerator. So this relationship is this one, HS is RE divided by GIS. Okay? This is a very simple expression. It's directly coming from this and this. This is obvious, but the meaning of this is not obvious. Meaning of this is HS and GIS has this relationship. That means GIS is RE divided by HS. All right? But in log scale, in dB scale, this means GIS magnitude is inverse of HS magnitude plus RE magnitude. Okay? That is shown here. Suppose you know this. Somehow you already knew this. Then this is the magnitude curve of this HE, right? HE. And 1 over HE is just a mirror image of this, right? Is 1 over H. We are talking about one is in the numerator, the other one is in the denominator. Then there is just a mirror image with respect to this x-axis. All right? So we know this is the 0 dB. Peak value of HS magnitude 0 dB. So this one is this one, okay? But you need this additional gain boost to evaluate this. So the distance between two curves are just 20 log RE, okay? So you know this. Suppose this is the magnitude of transfer function. Then input impedance is above this 0 dB line and elevate by this much, and they have the same shape. That means if you are just to see this HE, right? Then you know if switching frequency occurs at this point, then this is the ideal operational point, which is impossible to achieve. Then if we operate in this region, you have GBS because GI has this slope, inductive slope, okay? And in here, this is increasing. Then this GI has this capacitive slope. So this area is GCS, GBS, okay? You don't have to watch this GI all the time. You are doing this all the time, right? When you are designing some resonant converter, first thing you want to do is you plot this curve to estimate the DC in DC out gain. If you know this shape, then you can figure out whether you will have GCS and GBS. Okay. I think I told you this before. This is the final conclusion. Okay. So GBS boundary can be judged by plotting this, but you don't have to plot this. You will plot this all the time. Okay. If we have this kind of relationship, if switching frequency is somewhere here, then you have this type of GIS characteristic. Then converter will be in GBS region. Otherwise, converter will be GCS region. Okay. So this region is inductive region. Current is behind the voltage in phase, and this is capacitive region. Current is ahead of voltage in phase, right? So factor is positive slope of GI can be used to judge the operational mode, or negative slope of H will say same thing. Okay, so you don't have to use GI. Okay, just take a look at this. If H has the negative slope, then that region, that if the operational frequency is set at that region, you have GBS operation. And otherwise, you will have operation. 수업 중. I'm in class. My son. Okay, one is GBS operation and GC operation. This can be applied widely or universally. Just take a look at this, okay? Just to watch the slope of this DC conversion curve of any, not this one, not this simple one, any. Series resonant tank without looking at the GI. Okay, forget about GI for now, for this purpose. Just take a look at H only. That all the information is there. You don't have to watch GI. Okay? Okay, so this is the second use of the AC model. First, we use that model to evaluate the DC in, DC out gain, extremely simple manner, and we used that model to sketch the asymptotic plot of the GI that will provide the information of operational mode. Okay, and we found out the same equation, same information is also available from this HE alone. Okay. Another important information from the AC model of the resonant tank is this converter efficiency, right? So in evaluating converter efficiency, we are assuming this resonant tank is not ideal. It's practical, lossy. It contains many parasitic resistance. It really doesn't matter what kind of structure it is, how complex it is, the gain formula, the gain formula, the efficiency remain the same, right? So gain is defined here, gain from the input port and gain, power from the input port to power from the output port, okay? These are defined from the DC part. So this is the DC. So P in is this one times this DC voltage and average current at this path, which is this. Okay, P out is multiplication of this out voltage and the current coming into this port, which is I/O. Okay, so this is the DC in. This is calculated using only DC variables. This is also only calculated with the DC variables. Okay, then we have this AC component in between AC circuit. Then you need to find the relationship between from this DC value to AC value, right? Okay, let me explain just one thing. Okay, this is the VS. It's already known. And this IS is a DC component of this current, average value of it. That is related with magnitude of this by this simplification. So this is the magnitude of this tank current. And we have the factor of 2 divided pi and cosine theta. All right. This is the P in, power coming from the input port. And you calculate this. This is very simple, extremely simple algebra of complex variable or something. So you can follow this. Okay. So RE, I don't want to go through all the details. Okay. This one is very, very simple. You can figure that out. Okay. Later on. This RE means, this means what? Real part of something. This means real part. Real part of, okay, real part of IT1. Okay. IT1 is the first harmonic component of tank current. That is related with, this is the VT1, first component of tank voltage, times this is admittance, input admittance. Okay, so everything is so simple like this. And this YI is complex variable. In general, this YI and the GI is complex because we are assuming this is the arbitrary circuit, maybe contains some resistive component. So it consists of a real part and the imaginary part. So this one is complex impedance or admittance. Okay, then you follow this, very, very simple. Then the P in, you are putting in, is expressed like this. Okay, this is DC in, DC input voltage, and this is the real part of admittance, evaluate at the switching frequency. All right, P out is this one. Okay, this is a DC, and relationship between IR1, which is the AC current, to DC voltage is, you have factor 2 divided by 2 is coming here. And relationship between this fundamental component of this voltage to DC value is, you have this factor. So with this, you calculate this. All right? Then result, efficiency, final efficiency will be P out divided by P in. This one is inverse of P in, okay, because P in is coming in the denominator. So you need invert this expression, and this is P out, right? Then everything simplifies. The final result is this, right? Final result is this RE is this effective resistance. Since this port, you have some scaling factor with this pi divided 8 divided pi squared is coming here, okay? This equation is extremely good to use. Okay. So when evaluating efficiency, input to output of your entire converter, then just evaluate this. Okay. So this is a transfer function from here to there. Okay. Evaluate magnitude, evaluate switching frequency squared. Okay. And this is the RE, this one. And this is, you evaluate this and just take the real part of it. Okay. It comes in the denominator. Then this will give you the efficiency of your converter. Okay. Very simple, right? So, of course, this one is based on the sinusoidal approximation. So it will have some error, but very close to the real value. Okay. When this is the ideal tanks network, then efficiency should be what? 1. There is no power loss. Okay? So ideal lossless resonant circuit. Obviously, efficiency is 1. That is so obvious. You are assuming everything ideal. But if there is some parasitic resistance here, this formula will provide you the good approximation of the efficiency of entire DC-DC converter. And this result is applicable to any series resonant converter. Okay, it does not have to simple this RLC type. Any complex circuit can come here. Okay, as long as they have 1 incoming path and 1 outgoing path. That is the series resonant tank. So this one is applicable to any series resonant tank. Regardless of the complexity of the tank, it's just a matter of evaluating the input-output transfer function of AC circuit. Any boy. Okay, let me show you one example. Okay. This is the AC model of series resonant tank, but we have this L, C, R, E, and we have 2 parasitic resistances. We have resistance in parallel with this R, this L. This can be considered as the core loss of the core used in inductor or core or something, any loss. Typically core loss. And RS is ESR of inductor and O capacitor. Okay? So this resonant tank circuit is practical. If you know this one exactly, then it will provide a good approximation to the efficiency of your converter. So we just evaluate this, just 3. This one is easy. This one is also easy. This one is also easy. Okay? You can use some circuit simulator. You put structure of this into your circuit simulator. Then circuit simulator will calculate everything for you. Okay? Or you use Mescat, just type equation, and Mescat will provide the curve. You just read the value from the curve and put numbers there. Okay? That is the one way. Here we evaluate everything. Okay? So this is the HS expression with these 2 parasitic resistance. Which one is this? And this is the YIS admittance expression with 2 this parasitic resistance. Looks complicated, but it really doesn't matter. So that is just a matter of calculating some simple complex algebra and efficiency is shown here. Okay, so this is efficiency. This is the plot. Okay, I took this example from Erickson's draft. Okay, so that should be correct. That should be accurate. So maximum efficiency of that inverter is 1, obviously. But we have these 2 parasitic resistance with this curve looks like this. This is the maximum efficiency we can achieve. RS was, I'm sorry. This one is RS, this one is RP, parallel. Resistance, series resistance, okay? So maybe you have some numbers, you can estimate the maximum efficiency you can achieve, and efficiency goes down if switching frequency increases toward the higher frequency, and it will be saturated at some point, and this is the volts efficiency. You can achieve RE divided by RS plus RE. All right? Okay, so you may know this. If switching frequency is smaller than this frequency, efficiency will be good. Okay? If switch frequency is below this frequency, the converter will suffer with low efficiency. That information is shown here, and this cutoff frequency is, you can figure this out, is given by this. All right? So this curve depends on the resonant tank circuit, but numerically you can easily plot this and you can estimate the efficiency of your converter at different switching frequency graphically. Okay? That is the second use of that one, that AC model, and there are many other utility of that model. Okay? It carries the essential critical information about the inverter, which is the same as the converter. Okay? Okay. Okay, so I have two handouts. All right, so this should, okay, so look at the handout, first one and second one. All right. So first, I'd like to talk about what handout is about. Previously, we discussed this. This is the curve, or the DC in, DC out gain of series resonant converter. So this is the switching frequency is exactly at the resonant frequency. This is above resonance, and this is below resonance. I said there are some deviation, and this is a huge deviation for this. So we'll address this. So look at this. This is the curve of DC in, DC out voltage gain. This is the exact expression based on the Erickson's formula. He derived the formula. Maybe the other people derived that, and Erickson cited that in his book. Okay, let me show this. This is curve. This is curve. This is another frequency response curve. This is a gain curve. This represents the gain from DC in, DC out at this frequency is 1, right? So at this frequency, this is above resonant frequency, but it shows very systematic behavior. This thing looks like the resonance with different Q. So this one is okay, for the above resonant frequency. But if you go to the below resonant frequencies, this part might be okay. This part it looks like resonant curve, but you have another peaking here, This is called the subharmonic operation. And if Q is relatively high, even with this below resonance operation, Q is high. This is predictable. But if Q becomes small, it shows very strange behavior, like that, right? So this is the result of the plot of exact voltage gain curve, DC in, DC out curve, in comparison with the curve we went through. Okay, this is the part of the gain curve below the resonant frequency. Okay, if I overplot the above the resonant case, maybe they will be about the same, like this, right? So let me go back. This is the gain curve for this region, above resonance, below resonance, and this part in this purple box is shown here, right? So we have three cases, Q of 2, Q of 10. So Q of 10, this prediction is very good, very accurate. Q of 2 shows some deviation, but still observable. But Q of 0.5, this red one, is prediction of exact curve. Prediction of exact curve shows the gain is just 1, is not controllable, and it suddenly goes like this. Okay. Then we saw this part just so this area, squared area here. Okay? So previously the exact curve with Q of 0.5 is this horizontal line. This is the prediction of first harmonic approximation. So this is absolutely wrong. Okay? It's just garbage. Garbage in, garbage out. Okay? The reason for that is in this region, the converter went in strange DCM operation. Very strange. DCM means sometimes the channel is conducting and there is no current for a while and diode is conducting, something like that. Maybe they skip the cycles, several cycles sometimes, very strange, and suddenly the current is rising up like this. I think I told you last time, some strange behavior. Okay? There are many modes here, DCM. Type 1, Type 2, Type 3, Type 4. Okay? So if you avoid this part, that is okay. Okay? If you operate your converter always in this region, that is fine. Okay? But in the past or even now, for the high power application, you cannot use MOSFET because of its power rating is not that big. So for the inverter or converter, for the tower crane, some heavy industry construction, you need a huge one. Okay, I saw some inductor was this size. Okay, for that we cannot use MOSFET. You should use some other device which can carry huge current like GTO. Okay, I don't know the details about the GTO, but GTO should operate this region. Okay, because the GBS is very bad for that device, and the GCS is very good for device. So that converter, you should operate in this region. Okay, then maybe you select the operating point somewhere here. Okay, then this Q is proportional or inversely proportional to load resistance for the line node situation or heavy load situation. Then operating. The switching frequency fixed here, but operating point can be located here, depends on the value of the load. Okay, that is a very, very challenging scenario. Okay, so many people, they studied operation of this resonant inverter or converter in this region. In this region, using phase plane analysis, state plane analysis, very complicated analysis. But now, for your case, you don't have to worry about this one. So always select operation above the resonance. Then you have this characteristic which is closely predictable from that simple AC model. Okay, so that is one thing. Okay, let me explain this. Subharmonic operation means operation below resonant frequency. Okay. This is the situation. You have this half-bridge series resonant converter, okay, and this R is selected like this strange number. Then this RE becomes 1, right? Because the divided by this is the RE. Then this is 1, okay. So this is smart choice, not strange choice. So you have this, and this is the switching drive signal, okay. So this is the switching drive signal. So this upper switch turned on for this period of time and turned off at this period of time. So this is the TS. TS is this much, but this the resonant period. Okay, inverse of resonant frequency is much shorter than this. What I mean is this is one switching frequency. Switching period is 3 times of this. No. This is the switching period, right? And this is resonant period, 3 times resonant period. So we are operating with this condition. TS is switching period. This is resonant period. So if you flip this over, you have this expression that this means you are operating 1/3 of the resonant frequency. Okay? Usually the switching frequency can be placed, should be usually placed around the resonant frequency, but you can put that resonant frequency 1/3 of resonant frequency, then fundamental component will be die out, but third resonance will excite the resonance. Then still you have some operation, and converter will generate output voltage. That kind of operation is subharmonic oscillation. Okay, the book said that this subharmonic oscillation is desirable for some case. I don't understand exactly, but in some case, people prefer to you operate this switching frequency is at the 1/3 of the resonant frequency. So I plot that situation. This is the switching frequency, okay, which is 1/3 of the resonant frequency. So switching frequency is here, and resonant frequency is here. Resonant tank respond like this. So this third harmonic at this switching frequency, which is 1/3 of the resonant frequency, will trigger this one, will excite this resonant tank. Then the magnitude of this is at the fundamental frequency 2 divided pi. But in third harmonic, you have a factor of 1/3. Which one is this? So this magnitude is reduced, but this amount of this sinusoidal component excite resonance, and the output will be generated. Okay, this is still okay. The gain of this application is just 1/3 of normal operation, but still okay. Still it works. Okay. That feature is shown here. So this is the switch drive signal, but resonant frequency, the sinusoidal component which is exciting the resonant tank is this one. 3 times of that frequency, and this is the rectified version of it. Okay, so this is the current through here, and the average of this will go through this, and this times this resistance is the out voltage. Okay, so then our voltage will be this one times 1/3, right? So compared with the operation at the resonant frequency, just the DC gain is reduced by 1/3, right? That figure is shown here. Okay, so this is the operation at the resonant frequency, and this is the operation at the 1/3 of the resonant frequency, operation at 1/5 of resonant frequency. Right? I confused with this curve a lot because this axis is just the DC gain. It's not a frequency response curve. All right? So this means gain at this frequency. That is not what this plot says. It says if you operate at this frequency, DC gain is just 1/3. Okay? So this is another frequency response curve. Right? Just DC voltage gain. Right? This indicates if you operate this converter at this frequency, which is 1/3 of the switching frequency, then voltage gain will be 1/3, which is 3 times smaller than this one. That is the message of it. All right? So this is one simple example, but as I said, this is with some large Q. If Q got reduced, then there is a curve is different from this pattern, shows some strange behavior. That strange behavior is shown here. Right? So this part, this is the above resonance operation, below resonance operation. With Q of 2, you have this nice curve. Right? This looks like normal, what we are predicting. Okay? The right-hand side of this curve, converter is in CCM. That is called the CCM. That current, tank current, is existing all the time. Okay? But this side is DCM. Very strange behavior. Maybe many different curve. And if Q is smaller than 0.5, there is some this dead zone like this. Our voltage remains the 1 all the time, and it behaves like this. Okay, so that part, as I said, this one was shown in the previous curve. Okay, in this purple square, purple box is translate this. That is the relationship between exact analysis, result of the exact analysis, and prediction of fundamental frequency model. Okay, so if we use MOSFET, okay, most of people they are using MOSFET, maybe SiC MOSFET, okay, they are the same. Okay, SiC MOSFET, gallium arsenide MOSFET. With the MOSFET structure, you are saying, right? So we will be somewhere here and maybe somewhere here. Don't decrease Q too much, then the DC gain will be predicted, and the circuit won't show any abnormal, destructive abnormal behavior will be prohibited, right? That is the message of this analysis. Okay. From now on, we assume our converter or inverter is somewhere here. Okay. So we trust the AC model, right? Then we proceed all the analysis and set up design procedure based on the first fundamental frequency approximation, right? So that is the reason why maybe 90% people, they accept the fundamental frequency approximation, and they use to analyze their converter and to design their converter. Okay? All right, I think that's enough for today. We stop here. Thank you.